So for the second talk today, we have Agustin Somacal, that will talk us about the edge adaptive method and machine learning for high resolution reconstruction from cell averages. So
thank you very much.
Yeah,
Pretty long name. First of all, yes, this work is together with my director and co-director, Albert Cohen and Ogamura. It's still in developing, but we have some results, and I'd like to tell you a bit about it. And also, thanks for the organization of the conference. It's pretty nice, and I think many good things will come of it. I hope next year we'll do it.
Yes.
Well, you didn't tell. So, first of all, which is our problem? What was the thing we want to solve? The idea is that we want to reconstruct a function, that's the objective, and the thing that we will have is information about this function that has cell averages. So the idea is that we have like a mesh that will be not so high resolution, but low resolution mesh. And from these averages, we would like to reconstruct the function that supposedly lays behind. And so the information will be basically the integral of this function that is unknown, but we have access only on this. And this is important, maybe, for example, image processing, for going from low resolution to high resolution. And also it's relevant in finite volume schemes to solve PDEs, where once it has many steps, but one of the steps is once you reconstruct, you can use this reconstruction to calculate the fluxes that will evolve and make your solver the differential equation. And so for these two main objectives, the idea is try to see what we can do to solve this problem. So the first thing, the function is sufficiently regular. I mean, if you have some hypothesis, you know a bit about it beforehand. You can try to reconstruct it just by fitting polynomials in some of the regions. And for that, it's just trying to take a polynomial. You can write it with the coefficients. In principle, they are known. And you will try to use an stencil around the cell you would like to reconstruct. So we will try to reconstruct cell by cell. And so we will look around the cell, the averages, and use them to fit the coefficients of the polynomial that best fit all these averages. And well, if it is regular, it will be maybe a pretty reasonable approximation. And well, this procedure here represented in 1D because it's easy to see, but in principle you can do it in any dimension. But this in principle is solved, let's say. The thing that we are interested in is what happens when you have like a discontinuity. So we have something that is regular and suddenly bluff, but we cannot see it because in truth we only have access to the information of the average. So we can maybe know that somewhere there may be some problem. But still, if you will try to reconstruct here with a polynomial, the reconstruction will not be as good. But one thing you can do, and it has already been done, is, okay, you can take the approximations you got from both sides and try to extrapolate in the middle of the cell to build an approximation, and you still can do something. So in 1D, this is kind of done. But the problem is in 2D or more dimensions, because now this discontinuity will be like something, will be a curve, and this curve starts to be more complicated, because you need to parameterize this curve. A priori, there are as many curves as you would like to think about. And so you would like to, okay, a priori have a decision, say, okay, I will try to fit these things with lines, or quadratics, polynomials, circles, or something, to try to first find this curve, and afterwards try to find the reconstruction of your function. So this is the problem that we will try to solve. And for our case here, to tell and study, we will use piecewise constant functions, so we have the assumption that this will be 0 and 1. And in the middle, well, you will have some value, intermediate value. And with these values around, you would like to know, find which are the parameters of your curve that tries to fit, well, trying to find the vector of this continuity. Okay? So, okay, that's to say that afterwards, when you have like a fine volume scheme, once you have the reconstruction, then you can use it to evolve your equation. For example, there is transport and you want to transport the flux, so you can like calculate the flux and pass it to the nearby cells and well, use it as part of the scheme to solve the differential equation. And well, the question is, okay, you can do all this process of fitting a curve and then calculate the flux, but the question is, can you do it also maybe with directly learning the map from cell averages to flux? Okay, so this is a bit of the scheme, the pipeline scheme that there is behind. So we have started the cell averages that are given, because it's the image or the initial condition of your PDE. You will need a first stage to classify where in the domain there are the discontinuities, or maybe the discontinuities, so then you need some kind of detection mechanism. We say, for the moment in this case, we say that we know where they are, but it can be also part of the problem to think about. Then you have to create, like, fit these polynomials in the regular places where there is no problem, and create stencils around the singular cells to try to reconstruct by a curve fit and make the reconstruction. So that's a bit of the stages, and we'll focus on this part. So these are works already been done about how to fit lines. There are two different methods, and we will extend this method to fit polynomials. There is no machine learning there. And then we are trying also to see what machine learning can do in this part, just to, because we have to build on this thing, and then the idea is to go forward. So this is like the first stage. But the idea is to say, okay, well, now if this is working or not here, maybe it can work or not in some other situations. It's the first test. So, linear interface reconstruction. So we start with, now we will think, we'll say that we have the curve that we will reconstruct are lines. I mean, the curve that is behind can be something else, but we use lines to reconstruct. So this is our parameterized curve. And so the first some work that was done before is saying, okay, let's take the stencil around the central cell that is singular, that has some discontinuity. And the thing that we will try to do is say, okay, I can take a first curve that we will try to fit this, and I will try to do is to minimize, change the parameters in order to find the curve that minimizes the reconstruction error over this small stencil. So this is meaning that if I have a curve that goes like this, that definitely will make a lot of error, and if I start to get like this, it will get less error. Still you will get error because the curve that is behind is not aligned, but you will have something that is mostly linear. And so, well, for the test cases that we will show you, the function that is behind is the circle. This is how it looks, for example, with a certain discretization, the cell averages. This is basically the thing that we are given, and we want to reconstruct that. Okay? So, this is the first thing you can do, just baseline, is piecewise constant reconstruction. So, if you give me the cell averages, I give you the cell averages, I do nothing, basically. But it somehow tells us, okay, if we cannot do better than this, definitely we can do nothing. So it looks like this, and here we can see like the convergence reconstruction. So if we start to augment the number of discretization elements, then we will get more and more near because we are like refining. But well, you can the convergence rate is basically 1 because it's just refining at the same velocity as we are refining. Well, what happens when we do this optimization procedure? Well, we are now fitting, as you see, lines on each of these border cells. And we perform an optimization to find which is the best that minimizes the error of reconstruction around the cell. So for this, it will be on the stencil. For this, for example, is minimizing the error on the stencil. And you see that, okay, it's pretty, I mean, it's finding more or less the circle. However, there are some things, because for example, all the times it's like going pushy to the inside. So we are losing something. And this is because when we use this minimization problem, we are just trying to reconstruct in all the 3x3 cells. And so the best thing it can do, because the convexity, I mean the concavity of the function goes like this, it will like push to to the inside, I mean the optimization. So if you change maybe the norm, the weights over the 3 by 3 stencils, maybe we can push it outside again. And so basically it's trying to say, okay, try to find the curve that fits best there, but conserve the area that you have observed there. So basically you put a lot of weight in the central cell, and in the rest of the cell you will use it just to find the direction. And when we do that, okay, it's pretty reasonable, pretty nice. And we see the conversion rate. Well, first I haven't said, but yes, this will be order 2. And the rate is basically the same, but we gain almost 1 order of magnitude just by changing a bit how we weight what we are observing. Okay, this is very nice, but there is a problem that this is very costly in terms of time. You see, compared with the piecewise constant, this is in numbers also of discretization. So the more discretization, the more time it will take to make the fit. This is a much faster way because it's just you give the same thing. And this is like doing the optimization all the time, so it takes a long time. So we want to find something that is a bit better than that. And that's where LVIRA comes in. And the thing is, try to avoid optimization, and what they realized at that point is that in truth, with these 3 by 3 stencils, you could just calculate finite differences between pairs of columns. So if now I like, for example, take this, I think it's like a matrix, and sum the values that are in the column. So this will give me, like for example, here I have these values, it's 0, here is 1, and so here I have something intermediate. And so this, the sum will be 2.25, and so this gives me like this small column. And so what I can do is try to think of this like something I can fit in one dimension now, and say, okay, which is the line that tries to reconstruct these things. So now we pass from 2D to 1D, in a sense, just momentary, to find which is the line that will be better there. And if I do this for these two, and the others from the other side, it's 6 just calculations. The best option will be inside there. So in the end, instead of doing all the process of optimization, you can just calculate these 6, and one of them will be the optimum. So at the end, you still do a reconstruction and try to see which is the best, but only between 6 and not doing all the process. And so with this, we obtain this thing like that. So pretty nice. I mean, you get a nice figure, and the conversion rate is the same, and it's in between the two. So pretty good, and definitely is much faster. It's almost as doing a piecewise constant approximation. So pretty good. So what's next? The thing is, okay, we have this. There were also works already done with machine learning to try to calculate the flux, and we say, okay, let's see, try to start to compare and say what can do machine learning here. Still, maybe it's not super interesting because already kind of been solved, but it can be the starting point to go further. And so, well, first, the idea of building the dataset, the thing we will do is, okay, think again, we have a 3 by 3 stencil, and we build a dataset in which we will have 3 by 3 stencils with different curves, and from the other side, and we'll get the cell averages, and from the other side, what we want to learn is the parameters that have to go with these cell averages. So the neural network should take these 3 by 3 cell averages and give us the parameters of the curve that should fit. So basically the idea is that avoid the optimization problem. I mean, in an offline stage beforehand, we have to train the neural network, that will take time, but we will do it beforehand, and then we just go and use it to obtain the curve, the line that best fits these cell averages that are observed. Well, there are many ways of parameterizing this, but it's not maybe so relevant at this point. And the thing is that sometimes if you add some noise at the beginning, it can be a bit more robust what it learns at the end, and that we observe it can help a bit sometimes. And so this is what we get with the neural network. So also pretty nice. And when we see the conversions rate and compare with the others, we see that it's almost the optimal case we found before doing all the process of optimization, but with with a time that, okay, it's a bit slower compared to LVIRA, but still is like orders of magnitude best just doing the optimization, which is okay, pretty nice. So good, but the interesting thing also, like for me at least, is that we have only trained the neural network with lines. I mean, it has never seen circles or curves. And anyway, it had found a way to, when I give these larvages, it finds something that is almost the optimal, which is, I mean, I don't know, seems for me a bit interesting. But for the moment, we have not explored why exactly this happened that way, but it's interesting to see. And so, the next thing, now it's, the idea is, okay, we have all linear approximations. Can we do a bit better with something that is non-linear, particularly? Can we go try to fit polynomials to the curve? And so the idea is coming back to this idea, we have the stencil of 3 by 3. And we can think, once we are here, we forget that we are in 2D and we just sum the columns, and so we get these values. And so when we are here, we come back to the problem that I told at the beginning when we are in 1D. And so you can just try to fit a polynomial here that reproduces these 1D set averages that we had just built. And with that, we can just use this to reconstruct here a polynomial. So in principle, as long as you have enough size of your stencil and associated with the polynomial you choose, you can build a polynomial. And so that allows to finding a stencil around your circle and try to fit. It's important, for example, in this case, that the curve should cross side by side. Because if you cross down, then, I mean, you could do it, you have to do much more calculations, but sometimes it's not clearly solvable, or maybe the computer gives you like 23 pages of an equation to see what happens when it crosses, because you have to consider where it crosses as a function of the averages, and it gets like super tangled. So if you can extend your box until it crosses from one side to the other, then you can do this. And maybe if you are in the other direction, you can just do the same in the other direction and choose which is the best of both. And in that case, you will get one of the two options. Okay, well, that's the idea of the explanation. And here are what would we get of conversions, and we get as a fit. You see here, well, in this case it's a circle, and it's pretty near the circle. And the conversions also is like almost 3. So we wins over the linear, which is reasonable, and well, it's nice to see that. And so, and in terms of time, it's pretty the same as the LVIRA linear one. So we are getting better things and with the same time complexity. And so, just summary and some conclusions. We have said this is our pipeline that we have been using to reconstruct these functions. We tried the machine learning in the case of fitting lines, and we extended this method to polynomials, try to fit polynomials around. Things that we like to do is say, okay, well, now that we have here this, and we saw that this was a bit better than giving like a good approximation from scratch. Maybe if we try also from polynomials, maybe circles or other curves that we can put in the machine learning pipeline, maybe it can help in certain situations. And there is particular relevance when there is vertices. Here we have a smooth function. What happens when you have like a vertex, or maybe if you have a problem like a PDE that has different levels, like 3 fluids, and then maybe you have a triplet point crossing. Well, these kind of things, definitely all these methods cannot deal, cannot treat. And so the idea is, okay, well, maybe machine learning there can do something, because it starts to be complicated to do any calculations around it. The other thing is, especially for PDEs, instead of doing all this process that involve, like you need to do many things and it takes a lot of time, just go directly calculation the flux and will repeat to solve the PDE. And this has been already been studied a bit here in the And they did something like this for lines and for some cases of vertices that are orthogonal. But well, the idea is to try to explore a bit more about this. And also during all this process, we build like a library, you can do these experiments easily. So eventually someone else can continue. It has not to go from scratch because it takes a bit time to like build all this process and try to generalize it to make experiments reasonable. It was a lot of iterations in the process. And so I think this is very nice. Thanks.
Thank you, Agustin, for the presentation. Is there any question from the audience?
Okay. Can you come back to slide 46 or something? Okay, for example, Stefan, maybe you have already said that, but when you start, for example, from approximating just one line or one polynomial, why you don't put a constraint in order to make the border continuous? So here the line.
Yeah, I mean here that is like not being continuous. I mean in principle, the thing is that a priori you don't know what this. I mean you have. I mean two choices. Maybe if you do it continuous, you may not be exact in the reconstruction of the averages all along, maybe. The other thing is that, especially because at the end we are focusing more on the idea of doing solving the PDE, and we will calculate the flux. The only thing that we really care at the end is that it's conservative in the calculation of all this. So in truth, it's not, at least for us, it's not so relevant that it will be continuous on the figure, but there is some good approximation of this continuity that will allow us to calculate afterwards the flux. So very, but you could enforce it. But then okay, the other problem is that if you do that, you will need to add some global optimization thing because you need to tangle all the things together, and it will be probably not so nice to I mean, maybe yeah, I don't say it's not possible, but here we are like always forgetting everything and concentrating locally. And locally, I mean, you can do this. Otherwise, you will have like, for example, you can do, for example, splines around and trying to minimize the splines over it, but it needs to do like one optimization.
Okay. And sorry, another one. Next slide.
Mm-hmm.
Okay. If I understand correctly, the LVIRA and optimal linear interface. So the yellow one and the orange one in the top of the plot. After
this one.
1000 discretization boxes, they start to decrease the computational time, right?
Yes, I mean this I have not checked, but the intuition I have, because in truth this plot did it this week because hey, I should put a plot about the time, and then I saw this like, hey, wow, it's interesting. The thing is, I think it's because when you start to discretize more and more your domain, things start to get more linear in the sense that, like Taylor approximation. The more you zoom, the more linear the things you are seeing them, and the thing is that this optimization at the beginning you start just doing some averages to get like an initial point, and at some point, if the initial point is already near to the optimal, you don't need to do many steps in the descent. So that's why I think this goes like this, and this takes a bit more of time because in truth, here, you saw you already start like far away in the sense because you are. Well, there was super. Here, you instead of trying to reproduce the thing that will be the best, basically the optimization is taking you out from the. So you start near the optimal in the other sense, but then you are moving up. So that I will say is why these things start to converge together. And also because here is the averages, the time not only on calculating the singular cell, but also on calculating the other regular cells that are like standard. And so also the more the dimension you augment is to the number of cells that you have to do all this process, it's less compared to the number of cells that it's just right. So it's in combination.
Okay, thank you.
Are there any other questions?
So are the cell size always square, or can you have?
Well, that will be a nice question. For the moment, it's only squares, but eventually it will be interesting, and that's why maybe also I'm interested on machine learning, because in principle, all these calculations, you can do them because you are in a square cell and you can integrate and everything, but you start to have triangles or meshes.
Because like you were doing on circle, let's say if it was a crescent, so you have a sharp point, and basically in a small area you have a lot more variation than like, you know.
Yeah,
So,
the idea is, for the moment it's square, but if you go out from that, I mean, all the other methods that are non-machine learning will not work. You will have to do something else.
So, are there any other questions? So,